This is basically video 3.5 because last time we talked about NFAs, but to really round out the discussion, I'm going to need to talk about how DFAs and NFAs are related. So it turns out that every DFA can be converted to an equivalent NFA. And this kind of makes sense because every DFA can be turned into an NFA that just accepts the same language. And the way that this would work is if you had the transition function delta, which is associated to the DFA, on a state Q and A goes to another state P, then the NFA is just going to be basically defined on the state and the set that it goes to, because remember it goes to 2 to the Q instead of Q now. So this basically means that the NFA is always in a state set which contains exactly one DFA state, and that's the state that the DFA is in after reading the same input. What is more surprising is that every NFA can be turned into an equivalent DFA. It doesn't really seem possible because NFAs have these extra powers, missing or extra arrows and these epsilon transitions, but for any NFA, there is a DFA that accepts the same language. So if you can prove this, then you know that NFAs and DFAs are equivalent because DFAs can be turned into NFAs and NFAs can be turned into DFAs. The proof to show that NFAs can be converted into an equivalent DFA is called the subset construction. It was created by Michael Rabin and Dana Scott. And the number of states of the DFA that's equivalent to the NFA, unfortunately, can be exponential. Good. So this is very unusual, by the way, that an NFA can be converted into an equivalent DFA. I just also want to take a moment to point out what it means to be an equivalent DFA. NFAs and DFAs can recognize the same languages, so that's what it means for them to be equivalent. Remember, a finite machine M recognizes the language A if A is equal to the set of W such that M accepts W. For every DFA that recognizes the language A, there is an NFA that recognizes that language, and vice versa. Because the languages that DFAs work on and the languages that NFAs work on are exactly the same, it turns out the amount of stuff NFAs and DFAs can express is exactly the same. Now, it's relatively straightforward as to why DFAs can be turned into NFAs. You just throw a little bit of set notation on there. But the other direction is a little bit trickier. That's what's called the subset construction. In our previous NFA example, I tried to write out the transition function for the states and all the letters. But it didn't look exactly like the way a DFA would because I had these states that actually were not able to go to other states, right? So because I had this ability to go to different subsets. So remember, for an NFA, the delta function is defined as going from Q cross sigma union epsilon to 2 to the Q. So this left-hand column of Q1, Q2, and Q3 looks fine. To really clarify this function, I should have it defined on epsilon, but this is not actually necessary because this NFA doesn't have epsilon transitions. And what's really important here is that 2 to the Q includes elements like Q1, Q2, and the empty set. But those are not elements of Q. So right now, this is totally the transition function for an NFA. But to have it be able to be a DFA, I really need these to be states and not sets of states. That is where the subset construction comes in. The basic idea is going to be that the sets of states are now just going to be states. What's going to happen is I'm going to build this up just following the machine, and it's eventually going to give me a complete description in terms of sets of states. So let me talk about what I mean. I have delta, I have 0 and 1 as before. My start state, rather than being just Q1, is the set including Q1. Now, if I try to move from Q1 and on 0, I notice that I can either go to Q1 or Q2, and on 1 I can go to Q2. So this created new states. Q2 we've kind of seen before, just I put some brackets around it. But now, a new state that I have is the set Q1, comma, Q2. All right, let's continue building up. So from Q2, if I follow the 0, the only state I can get to, it looks like, is Q3. And it looks like from Q2 on 1, it doesn't look like I can get anywhere. Now on Q1, comma Q2, I know that I can get from Q1 on 0 to Q1 or Q2, but I can also get to Q3. And now similarly from Q1, Q2, from Q1 on 1, I know I can get to Q2. And from Q2 on 1, I can't get anywhere, so that ends this state. Now I have a state that represents everything, which is Q1, Q2, and Q3. And now on 0, I know that I can go to Q1, Q2, or Q3. And on 1, it looks like I can go to Q2, because Q1 goes from Q1 to Q2 goes on 1, and then Q3 on Q2 goes back to Q2 on 1. So that's that. Now the last one I didn't write yet is, of course, the set. That's just Q3 itself. Q3 on 0 goes back to itself, and Q3 on 1 goes to Q2. All right, so now I have a complete table of states. And in this case, this is a full delta transition function. It's just that delta, the states, are just going to be sets of sets, right? So Q1, Q2, but then also Q1, comma Q2, and Q1, Q2, Q3, and Q3. Oh, and then I guess for completeness, although it's a little bit weird, I should have the empty set. From empty, you can't really get anywhere. Okay, so let's, now that we have these states, let's go ahead and build and draw out this NFA, which is going to have 1, 2, 3, 4, 5, 6 states. Great. So what I've done here is copy over the transition table we made on the previous slide And I've drawn my new states, which were originally sets of states. So let's go through and start looking at the transitions. From Q1 on 0, I go to Q1, comma, Q2. And on 1, I go to Q2. Continuing on, from Q2, on 0, I go to Q3. And on 1, I go to the empty set. Then, on Q1, comma, Q2, on 1, on 0, I will go to Q1, Q2, Q3, and on 1, I will go to Q2. Then, from Q1, Q2, Q3, I can see that it loops back on itself on 0, and it goes to Q2 on 1, and then I have on Q3, it loops back on itself on 0, and it goes to Q2 on 1. And for completeness, I will also have this empty set, which will just loop back on itself on both 0 and 1. Okay. So the critical point here is that the DFA states that you created have names that are sets of NFA states. And as a DFA state, an expression like curly brace P, comma, Q, close curly brace must be read as a single symbol, not as a set. And we showed that it was going to be a proof by construction. Given an NFA, we will construct an equivalent DFA. Of course, I have not actually proved it in general, but I did show you an example of why it works. To summarize the subset construction, we say that given an NFA with states Q, input sigma, which is the alphabet, the transition function delta sub n, start state Q naught, and final states F, we can construct an equivalent DFA with states that are the set of subsets of Q, has the same alphabet, sigma. It has the start state Q0, but it's just in braces now. And the final states are all those that were a member of F, the final state in the final states of the original NFA. Just to round out this video, I have a memory matrix here where it would be a good exercise for you to write down what is the difference between the transition function, acceptance, determinism, and construction of an NFA and a DFA. And that's all I have for you today. So thanks for watching.